Illustrating and graphing linear inequality in two variables. What is the difference between linear equation and linear inequality? We know that a linear equation with two variables has infinitely many ordered pair solutions that form a line when graphed. A linear inequality with two variables, on the other hand, has a solution set consisting of a region that defines half of the plane. And these are the examples showing the graph of each linear equation and linear inequality. For the inequality, the line defines one boundary of the region that is shaded. This indicates that any ordered pair that is in the shaded region, including the boundary line, will satisfy the inequality. To see that this is the case, choose a few test points and substitute them into the equality. The test points are 0, 0, 2, 1, and -2, -1. And these test points satisfy the given inequality, so all these solutions are true. Also, we can see that ordered pairs outside the shaded region do not solve the linear inequality. Sample test point, we have -2, 3. And 3 would be never less than or equal to 0. The graph of the solution set to a linear inequality is always a region. However, the boundary may not always be included in that set. In the previous example, the line was part of the solution set because of the or equal to part of the inclusive inequality greater than or equal to and less than or equal to. If we have a strict inequality greater than and equal, we will then use a dashed line to indicate that those points are not included in the solution. Non-inclusive boundary, we have a dotted lines, and in inclusive boundary, we have a bold straight line. Consider point 0, 3 on the boundary. This ordered pair satisfies the linear equation. It is the or equal to part of the inclusive inequality that makes it part of the solution set. Showing y is less than 3 halves x plus 3, the answer would be false because 3 would not be less than 3. While on the other side, we have y is less than or equal to 3 halves x plus 3, the answer would be true because of the word or equal to. Example number 1. Y is greater than x minus 2. Use any method in graphing linear equation. In this example, let's use slope and y-intercept. Slope is equal to 1 and y-intercept is equal to -2. Slope is equal to rise over run. Rise is 1 unit up because it's positive and run is 1 unit right because it's positive. Start from a point on the line, which is the y-intercept 0, -2. Notice that the inequality symbol is greater than, which means it is a non-inclusive boundary. So use broken line. Now, do the origin test to identify which region will be shaded. Take note where the origin is located. Substitute the value of the x and y. We have the answer of 0 is greater than -2. The answer is true because no negative numbers would be greater than 0. In the origin test 0, 0, the linear inequality y greater than x minus 2 is true, which means the origin is included in the solution of y greater than x minus 2. The shaded part is upper part or the above part of the broken line. Example number 2. Y is less than or equal to negative 2/3 x plus 1. Use any method in graphing linear equation. In this example, let's use again the slope and y-intercept. Slope is equal to negative 2/3 and y-intercept is equal to 1. Rise is negative 2 unit down because it's negative, and run is 3 unit right because it's positive. Again, start from a point on the line, which is the y-intercept 0, 1. Notice that the inequality symbol is less than or equal, which means it is an inclusive boundary. So use solid line. Now, do the origin test to identify which region will be shaded. Take note where the origin is located. Substitute the values of the x and y, which is 0, 0, and we came up with the answer of 0 is less than or equal to 0, which means it is true. In the origin test 0, 0, the linear inequality y is less than or equal to negative 2/3 x plus 1 is true, which means the origin is included in the solution of y is less than or equal to negative 2/3 x plus 1. The shaded part is lower part or below part of the line. Thank you for watching.